Speaking of like applications of integrals and stuff, so far, the way you've learned to approximate integrals, if you can't find an antiderivative, we've used like the trapezoid rule and the quotient rule, the trapezoid rule and Simpson's rule and stuff like that, right? You can also use something called an infinite series to do stuff like this. And do you ever wonder how your calculator finds like natural log of 5? Like, I mean, your calculator gives you a decimal for natural log of 5, right? But what the heck and why, right? Does that make sense? Like, how does it approximate this number? How does it give you that approximation in the first place? That's what the stuff we're going to learn in this chapter will, like, tell you what to do. It's going to say it uses if you look up the documentation, it's going to say it uses a Taylor polynomial of blah, or something like that. And those things called Taylor polynomials are used to approximate functions, and we'll learn about them in this chapter. But you need to know a lot of stuff to kind of get to that stage. Does that kind of make sense?
Okay. And then we can do your own calculators.
And then you can understand how your calculators work, which means you can kind of generalize it to situations where you want to approximate things. So I'm afraid I don't know how you use this in your engineering stuff because I don't know enough about engineering. Like, I would love to know that, I just don't. But I have a friend who's an electrical engineer.
I was relying on you, you let me down.
But I have a friend who's an electrical engineer, and I know he uses math all the time, so we'll go out and run and talk about math, and he knows all this stuff, and I'm like, holy crap, you know a lot of math. He's like, yeah, I use that stuff. So, I know EE is really big, really mathy, right? Other stuff I don't think is quite as mathy. It depends on what kind of, like I know if you're a civil engineer, there's a lot of probability in that. So, okay. So the first, and I know these chapters are out of order, but this is a long, semi-challenging chapter, and so we just don't want to put it at the end when you've lost all steam whatsoever. So here we go. So a sequence is a list of numbers written in a definite order. Okay, so we have A sub 1, A sub 2, A sub 3. And what those little sub things mean is like my first thing, my second thing, my third thing. Okay, does that make sense? And for every number n, there's a corresponding A sub n, and a sequence can be defined as a function whose domain is the set of positive integers. And so as in you have a function, instead of f of x, it's f of n, which gives you your nth term in your sequence. And the n's that you input are 1, 2, 3, 4, 5, etc. Like it's from a list of numbers, as opposed to a function when it's like f of x, then you can put in like things like pi and 1/2 and e and negatives as well, right? Does that make sense? If the function is defined for negatives, that is, right? Okay, what would a graph of this function look like?
Probably linear.
Okay, well, not necessarily linear. The kicker is with regular functions, you input whole numbers and also many of the intermediary values, barring some exceptions like rooting negatives and stuff like that, right? It's going to be dots. Does that make sense? If you drew a picture of this.
So it's dots and not piecewise?
Yes, the first number you plug in is 1, and then out comes whatever the value of your first number is. Then you plug in 2, and suppose that one's, some values up there. You plug in 3, and it jumps down and it's negative. So the numbers that come out are the values of the sequence. They can be positive, they can be negative, but the point is, if you were to graph this function, it's going to be dots and not a connected thing. And then ask yourself, is this a function? Does it pass the vertical line test? It does, right? Because every vertical line you have is going to only have one output. You're just missing a whole bunch of them in the middle.
Unless you accidentally circle back around.
There's no circling around. You have a first element, second element, third element. And it's okay if, say, your fifth element is equal to, say, your second. That still passes the vertical line test, right? You see what I'm saying?
No, it
doesn't pass the horizontal one.
If your 2 came out 3, 6, and 9.
Nope, your 2 term has to come out as one thing. So it definitely is a function in that sense. Okay, and we do assume that we start at 1 already. But if you think sequence list, nope, not. You could define this thing to start at 0, but usually sequences just begin at 1. Okay, list the first 3 terms. So sometimes you're given a formula. So a sub n is 2n over n plus 3, so a sub 1, the first term, is what you get when you plug in 1. So that's, really? Yes, I can't arithmetic today. 2/4 or a half. Thank you. What about a sub 2?
4/5.
4/5. And then a sub 3 is 1? Yes. Do you guys agree? 6 over 6, which is 1. Okay. So 1/2, 4/5, 1. It looks like as our n's, the number in the sequence gets bigger, these terms are getting bigger and bigger and bigger, right? Okay. Barely, but yes. And if we found one more, what would A4 be? Just do one more, just for kicks. 8 over 7? Is that bigger still? Yes, okay. Oh, your favorite trig functions. Cosine of n pi over 2. Okay, so a sub 1
Zilch.
is cosine of pi over 2, which is indeed 0. Yes, good job. A2
-1.
is cosine of pi, which is -1. A3 is
Zilch.
cosine of 3 pi over 2, which is 0. And let's just find A4, just for kicks. Cosine of 2 pi, which would equal
1.
And then what's going to happen after that?
Zilch.
It's going to cycle. Does that make sense? So this list, you could say it's 0, -1, 0, 1, 0, -1, 0, 1, and there's going to be that cycle of 4 that's repeating for this particular sequence. Does that make sense? Okay. All right, this is something called a recursive sequence. So, and I think this is an example of a sequence you might even know the name of. So let's just figure out how to work it, and then we'll deal with it from there. So, you ruined the surprise. Okay, so first 5 terms, and I already told you the first 2, right? I said the first term is 1. The second term is also 1. And then what the hecka does this mean? Okay, so what is a sub n minus 1 relative to a sub n? Before or after is the previous term. So this is the previous term. Does that idea make sense? How about this a sub n minus 2? Second previous. And I'll explain what I mean with numbers. So a sub 3, if you plug in 3, you get a sub 3 minus 1 plus a sub 3 minus 2, which is a sub 2 plus a sub 1. Does that make sense, how that plugging in 3 worked for that? And that means, so to find a3, you take the previous term and then the term from 2 terms ago and add them together. A sub 3 is equal to 2. A sub 4 would be equal to a sub 3 plus a sub 2, right? And so a sub 4 would be equal to 3. And how about a sub 5? 3 plus, that'd be a4 plus a3, right? Which would be 3 plus 2 or 5. What would a 6 be? Which is 8. And then 8 plus 5 would give you the next one, which is 13. I was once on an equinox marathon relay with a bunch of people in the math department, and we called ourselves the Fibonacci sequence. And when I ran by, they were like, 1, 1, 2, 3, 5, 8. What comes next? It was really great. Okay, so that's like a recursive sequence because you have to depend on the previous terms to get the later ones. That's kind of that's how recursive sequences work.
So you're always given whatever previous terms you need.
You'll always have, yeah, either you're told either I have to give you like a point to start with, or I'd have to give you like, this is what a sub 7 is, find the next 3 from there, or something like that, right? And in this one, it depends on the 2 previous terms. You've got to know the 2 previous terms to get the next one. And often, sometimes there are formulas that you can like make this into a formula, like the one we had for example 1, but I don't know how to do that right now, not off the top of my head.
Exponential.
This is, I'm not sure if it's not exponential. I think it's slower. I don't know if it's how growth is relative to exponential. I plead the fifth.
Okay.
Okay, same idea. A1 is equal to 6. And this one's indexed a teensy bit differently, but what this is saying is to find the next term, you take the previous term and divide it by 6. Does that make sense? So then a sub 2 will be equal to a sub 1 over 6. Do you see how that's, the thing on the left subscript is 1 more than the thing on the right, correct? I could have also written this, couldn't I? That achieve the same thing?
Yeah.
The relationship is still the same, right? N plus 1 is the one after AN, right? AN is the one after AN minus 1. So in that case, what is a sub 2 going to equal? 1. A sub 3 will equal a sub 2 over 6, which is 1/6. A sub 4 will equal,
1/36.
hold on a second. It'll equal A3 over 6. 1/6 over 6, which definitely is 1/36. Yep, sorry, I didn't mean to not believe you. I just needed to think. And a sub 5 will equal A4 over 6, so 1/36 over another 6, which is,
216.
good job, 1 over 216. Does that make sense? Okay. Alrighty.
It's kind of not the direction you want your sequence to be going.
Well, it depends on what you're doing. Like if it's going to 0, well, going to 0 is often a good thing. So
Debt. That's
Death?
what you want your debt to be.
that's where you want your debt going. Exactly. Yes.
1 over $216.
Okay. So here is the technical definition. So what we're good of a limit of a sequence. So you guys found limits of functions in previous classes, right? And the way that we found limits of functions is, you use things like, I don't know, specifically the stuff going to infinity, there was that whole, you can divide by the highest common power of numerator and denominator thing. We reviewed that on the first day. And there also was L'Hopital's rule, right? Those two rules were applying for things going to infinity. But here is the technical definition. So the limit is equal to some number L. If for some, have you seen this little epsilon bigger than 0? Maybe. If you haven't, it's okay. You've got some small positive number. There exists an M such that the absolute value of a sub n minus L is smaller than epsilon whenever you're bigger than that M. So, first of all, in dissecting this, when you first learned about absolute values, did you learn that they were distances? So this thing is saying the distance from a sub n to L is less than whatever that epsilon is. Okay, so here's the picture. You have some number L, and you think that your sequence is approaching that number L, which means your dots are getting closer and closer to that as your n gets bigger and bigger and bigger, right? That's the general idea. The technical thing says that here would be L minus epsilon, so epsilon below. Here would be L plus epsilon, or epsilon's above. And just think that epsilon's a really, 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 really small number. And I just drew this picture really zoomed in, okay? Here's that capital M thing. And what this is saying is that if you have some bitty small number, you can find a number, and after that point, the dots in your sequence never are more than epsilon away. So the idea here is you pick any bitty epsilon number, and then you can find some M, and after that M, capital M that should be, your a sub n's are plus or minus epsilon from your limit L. And for this, I think Jill has the best analogy. It's really great. She says that you have an adversary, and this adversary, who is your arch enemy, picks a super small epsilon, like 1/1,000,000th. And you say, oh, no, after I get past this point, I'm within 1/1,000,000th. And no matter how small of a number your adversary picks, you can always find a number such that after that you're within that little bit. That's the basic idea. We're not going to make you prove anything with that, but that's the idea of closeness. Is once you go past a certain point, you make a super small sort of, I don't know, fence around your values, and your values are stuck inside that fence. That's the idea. And what happens out here is irrelevant, because as you go to infinity, that's what matters. Okay. So that's the basic picture of what it means to have a limit. I should have reversed these. Oh well. Okay.
Oh, I see now why that should have been reversed.
Yeah, this should have been reversed, because this doesn't really pertain to having a limit, but it's okay. So this, before we move on to actually finding limits, sometimes it's good to have a closed form function that you're finding the limit of, as opposed to just a list. It seems like these things are going to get bigger and bigger and bigger, but it'd be good to have like a formula for what the nth term is. Does that make sense? So your first term is 5, your second term is 8, your third term is 11. How are you getting from one to the next?
Plus 3.
Plus 3. So let's just check. Would a sub n equals, now would it just be 5 plus 3 what?
N?
3n. And then check it. Now does that work?
Yes.
No, because when you plug in 1, you get 8. Do you see I'm kind of off by 1?
So it'd be 2 plus 3.
Yeah, so that doesn't work. So a sub n could be 2 plus 3n. Now does it work? When you plug in 1, do you get out 5?
I was starting at 1.
We have to start at 1. Yep, exactly. Yep, you have to start at n equals 1 is always the first number you plug in. Another way to accomplish that would have been to write a sub n equals 5 plus, excuse me, just need to erase that, 3 times n minus 1. It's the same thing, right? Which, when you simplify it, reduces down to this, right? But then when you plug in 1, n minus 1 is 0, right? And you have no 3's added to that 5. So I don't really have a spectacular way for you to figure those out other than to guess and check and try some stuff. And then check if your thing works by plugging in n equals 1, n equals 2, n equals 3. And I won't give you anything that's super tricky or even guess and check. Does that make sense? Not intentionally anyway. If it happens in WebAssign, please let me know. All right, this one.
Oh, this is like the 161 except for it's 1/4.
Yeah, but it's also, there's not necessarily a there's a negative flip-flopping. Okay, so let's say, first of all, if I put in a negative 1 to the n, will that accomplish the flip-flopping in the way that I want?
No,
Then when I plug in 1, my first term is negative, right? Do you see what I'm saying?
that won't work.
So how could I make it so that my first term is positive? And there are two ways to do this. Make it n plus 1. Does that make sense? Then when you plug in 1, you get negative 1 squared, which makes a positive 1. At least you got the flip-flopping happening now.
But how do you do this with an exponent? It looks like you're multiplying everything by negative 1 over 4.
Yeah, you are. Okay, so now let's look at denominators. So this is 4 to the third, right?
Yeah.
This is 4 to the squared. This is 4 to the first, right? This you could think about kind of as there's a 4 to the 0 on the bottom, right? And this you could think about as 4 to the negative 1, couldn't you?
So 4 to the n minus 2.
Here's how I would say this. This 1/64th, I think that does it, yeah. So 1 over 64 is 1 over 4 cubed, and that's, I don't know why I wrote 5.
That's a fifth term.
Exactly, that's what I was thinking. This is the 5th term, right? So would you agree with 1 over 4 to the n minus 2? you see what I'm saying? The relationship, fifth term, this is 3, right? That 3 is 2 less than the number term it is, right? This one, the denominator's 4 squared, it's the fourth term, right? 2 less than the number term it is, right? So a sub n is negative 1 to the n plus 1 over 4 to the n minus 2. Another way to write that would be this. You could have said 4 squared negative 1 to the n plus 1 over 4 to the n. Wait. Does that work? Yes, it does. Yeah, it does, definitely. Do you agree with that? Do you want to see how I got that?
No, it makes sense.
Let me just show, in case you're confused, let me show you how. That's the same thing as negative 1 to the n plus 1, 4 to the n times 4 to the negative 2, right? By that? And then if I multiply by 4 squared here and 4 squared there, these two become 4 to the 0, which is 1, right? So either way. But I think it probably is easiest to look at the relationship on that power of 4 and the number term it is. Does that make sense? Okay. All right, so here is the a pretty useful idea. So if you have a function and its limit is L, and if you have a sequence that matches that function, then the limit of the sequence is the same thing as the limit of the function. So, for example, your function, suppose we had f of x equaled, 1 over x, okay? That function looks like this, right? What's the sequence going to look like? It's going to be dots. It's going to be there, it's going to be there, it's going to be here. And this condition means that when you plug integers into that function, you get sort of just dots that are on the function's graph, right? And do you agree that, well, if the smooth continuous curve goes that one place, well, then so does the, right? Okay, great. And so that means you can use a lot of the rules you know for finding limits of functions to find limits of sequences. There's like the exact same thing. Okay, so like for this guy, limit as n goes to infinity of n squared over 2n squared minus n plus 5. Professor Fodry changed it to x's, and I don't think it matters, so I'm not going to. How do you, if this wasn't n's and they were x's, how would you do this limit?
Same.
You divide by
Divide everything by n squared.
n squared, yep. And that'd be 1 over 2 minus 1 over n plus 5 over n squared. So we're
Take it all
saying
to infinity, end up with 1/2.
divide by n squared, and you get a half. I know that a lot of you can do limits like this in particularly really, really quickly, as in you don't even need to do the work to know it's going to be 1/2. And here is the sort of general rule that I have. On your take-home quiz, show me you know this step. Does that make sense? Just that one step, give me the limit. On WebAssign, I don't give a crap what you do, other than you shouldn't Wolfram Alpha it. Okay, because we go on checking your answer, so to speak, right? Does that make sense? Okay.
Wolfram Alpha never gives you the answer. It gives you some weird way to get to it.
Sometimes it often, I don't know, I think it's pretty good a lot of the times. It's a really great checker. All right, this guy, so limit n goes to infinity, e to the n over n squared. Now technically this is the one instance where, at least in class, you've got to make them into x's. I have to plead the fifth and say that I haven't asked Professor Fodry how picky we're going to be about this, so I don't know about this yet. But for now, let's just accept that this is what we have to do. Because what rule are you going to use to get the limit of e to the x over x squared?
I don't remember the name.
The one we take derivatives, right? L'Hopital's rule. And L'Hopital's rule only applies to functions. So That's the sort of way you tell me that you've changed your n's into x's and you're using a function now. It's a silly thing. Okay, like, I get it. Like, what the heck? Why can I have a function of n? It's just letters. I know. I feel the same way. I record myself saying that. But for now, let's just change the n's to x's because sometimes people are picky about that. And if I'll ask Faudree if she really cares. Okay, I'm not sure I do, but I think it's because there are examples where it's actually, if you have a sequence that can converge, but the function will not. Like I don't have a good example on the top of my head right now. So for now, let's just say they're functions and we'll go with it. So limit x goes to infinity. What's the derivative of e to the x? E to the x over 2x, and then you do it again, right? And you get over 2, which gives you
Tends to infinity.
tends to infinity. So if this goes to infinity, what does it mean about the sequence? Diverges. Going to infinity isn't the only way to diverge, FYI, okay? Does that make sense? Going to infinity is divergence in a special way. But that sequence that we had that was bopping between -1, 0, and 1 also doesn't converge, because it doesn't go to one specific number. A sequence that converges makes up its mind and decides to get close to one thing. This thing just decides to get big. That -1, 0, 1 is like a politician that flip-flops between their ideals.
So every politician.
Oh, I know, just kidding. And flip-flopping isn't always a bad thing because you can actually change your mind about something. Like, that's okay too. But that one goes back and forth. All right, this one. So here.
New information, then you have to judge the situation different.
Is it possible to diverge to a specific number?
Yeah, well, no, if you go to a specific number, you converge.
Okay.
Yep. This limit is actually equal to, no. It's okay if you don't.
Do you want, right?
It's actually equal to E. And my suspicion is that most of you don't know why, right?
Is that how they calculated for experiments like that?
That is actually a one way your calculator could find E. It could take and like plug in bigger and bigger and bigger numbers for n. Like if you plug in like n equals 1,000,000, you're gonna get something close to 2.71. But let's actually prove it using L'Hopital's rule, okay? It's a little bit convoluted, but we'll do it. Let y equal 1 plus 1 over x to the x. Like I'm just giving the thing, I'm finding the limit of a name. Does that make sense? I just called it y. Whatever. What I'm gonna do now is I'm gonna natural log both sides of this thing I just wrote down. So I have natural log of y equals, can I say it as x times natural log of 1 plus 1 over x? Do you guys agree with that? Is that okay? Okay. FYI, stuff like this is done in section 4-4 of your textbook. If you want to go look someplace and see examples of this as well. There are more complicated ones done in that part of the book. So the limit as n goes to infinity of natural log, or sorry, x goes to infinity, excuse-moi. Limit x goes to infinity natural log y equals limit x goes to infinity natural log of, x ln 1 plus 1 over x. Is everyone okay with all the steps I did there? I changed the n's to x's, I just did natural logs. Now I'm gonna work with this thing here. Actually, this is infinity times, what's this ln of stuff going to?
1.
This is going to 1, and ln of 1 is 0, right? So infinity times 0, yes.
What are you doing on the left side if there are no x's?
That'll come back in a moment,
That one.
okay? So just for now, I limited both sides, okay?
All right.
What is infinity times 0?
Well, that's a great question. It's one of those indeterminate forms that's not always consistently something. 0 times any finite number is 0, but 0 times infinity is definitely not always 0.
Can you do L'Hopital's rule?
You can if you are clever about it, and here's where the cleverness comes in. ln of 1 plus 1 over x over 1 over x. So first of all, do you agree that the thing I wrote right here is equal to this?
Yes.
Yes. Okay, why is that crazy cattywampus thing actually helpful? What form is your limit now? Where's your numerator going? Where's your denominator going? Also 0, right? What you did is you took something that was infinity times 0, and you made it into 0 over 1 over infinity. Does that kind of make sense? Which makes it 0 over 0, so you can actually use your rule. And that's a really common trick with infinity times 0 stuff. Make one of them into a ratio, putting it in the denominator as 1 over junk. And usually you pick the easier, simpler function to do 1 over junk with. Okay?
Wait, how did you get 1 over x for the denominator?
Because I'm really, really, really awesome. I'm just.
So we took an answer to your question.
No. I mean, it's a clever trick, but multiplying by x is the same as dividing by its reciprocal. Does that make sense? And just think, if you go from this to this, I'd multiply by x, which takes me back to that. You see what I'm saying? If I multiply the bottom by x, I get 1. Multiply the top by x, I get this. So that's why it's just kind of doing your simplification that you would do backwards. And it's just a really clever trick, so you can now use L'Hopital's rule. Okay, so moving on. Limit x goes to infinity. What's the derivative of the numerator? Don't worry about simplifying it, just 1 over 1 plus 1 over x. That's the whole derivative of ln of something, right? Times the derivative of the inside stuff, which is
1 over x squared.
almost negative 1 over x squared. But, does that make sense? What's the derivative of this 1 over x in the bottom? Negative 1 over, oh, look at that! What happens to them negative 1 over x squareds? They go away. And now I have, this is equal to the limit x goes to 0, 1 over 1 plus 1 over x.
Where does x now go to 0?
X is still going to infinity. My bad. Thank you. Sorry.
That's just really confusing.
Nope. That was my mistake. Okay. So now where is this thing going?
That's what-
1. So, limit x goes to infinity, natural log of y is equal to 1. I said the answer was E. Right? I did, right? And I meant it. I
Oh,
found
that's
the,
because you.
exactly. I found the limit of the natural log, right? And the technical thing that happens is you can switch the ln and the lim, and that has to do with ln being a continuous function. But that's more of a real analysis-y thing you prove. And then how do you undo the ln to get at the limit? You e it, and the limit as x goes to infinity of y, which was the original thing, right, is equal to e to the first.
So, in order to figure out the definition of E, you need to use E? Or is E just the letter they use for this?
E is the letter they used for this, and that definition, that like limit thing, because E, they had to make something that was the inverse of natural log, right?
Yeah.
So, but that expression that you have there, you could plug in bigger and bigger x's and would approximate E. So that's a tricky one, right? But there are examples of that guy in section 4.4. Yes?
So can you technically, with any function, even if it isn't helpful, raise it to a base? Like, at y equals x squared, now you have 10 to the y equals 10 to
In
x.
general, you can apply this technique to lots of stuff. It just might not always be helpful.
Yeah.
Does that make sense? Like, it just might not be helpful to do so. The reason you can apply ln is partially because ln is a one-to-one function. There's a little bit of technicalities going on there, but ln is the only one we usually use. Yeah.
If you discover an irrational constant, do you get to name it?
I don't know. Never found one myself. Okay.
How about E plus pi?
Just shush. Okay. So, now, this idea that you can move limits inside of continuous functions lets you find limits of other things, like stuff like this. Do you want to find this limit? The limit as n goes to infinity of a sub n. So cosine, if that was just cosine of n and not other stuff inside, what does cosine do in general? It oscillates, or so it's going to diverge. But you can say this is cosine of the limit and in general, like on take-home quizzes, I want to see that like step being flipped for you guys. Does that make sense? Okay. And then is that limit inside the cosine a very hard one to do now? Technically, you just divide top and bottom by n. Great. So cosine limit n goes to infinity, pi over 1 plus 1 over n, which yields cosine of pi, which is -1. So a sub n converges to -1. And I think to say you've got a sequence, you put little braces around that, but since that limit came out to be a number, that's what your sequence is going to go to. Do you have any questions? You're making a question face.
Well, how did you get the 1 plus 1 over n?
I took this and divided the top and bottom by n. That's that whole dividing by the highest common power. Does that make sense? That's like we did with the one that was like n squared over junk that had n squared. Yep. Yes.
Why aren't you changing the n to x instead?
I'm only going to really require that you do that maybe if you use L'Hopital's rule. Does that make sense? Only if you have to do that rule am I really going to care at all. And that's maybe up for debate, okay? So don't worry about it too much. All right, this guy. Oh, this brings up a great point. The one thing that I saw on tests when I was grading is you was making up rules for logs. Stop it. Stop it. ln of e minus 1 is not equal to ln e minus ln 1, okay? No. Stop. Okay, I will stop right in a second. ln of, if you had a side of an equation, and the side of your equation was 20e equals, I don't know, 10 e to the t, and so then you say, okay, well, I have 2e equals e to the t, and then people said 2 ln e equals t. What mistake did they make there?
You need to do ln.
You need to ln the entire side, right? They kind of assumed that that 2 can come out of the ln. No.
No.
Don't work that way, I'm so sorry. Okay,
Give
so
me a power.
what is the rule, or what is the, and I know that those rules are tricky, so if you care, I can go over like why they work later, but when you have a natural log of a difference, what does it become? How many ln's are in the compressed version? 1. Becomes ln of 2n plus 1 over n. That's how logs get condensed. They condense with 1 ln.
Yes.
What do you think the most common mistake is?
Distributing the ln?
People, generally speaking, say this. That's actually different. You can plug in values for n and verify yourself that those two things are unequal, but this is actually, this is wrong.
Isn't it supposed to be natural log of 2n plus 1 minus natural log of n?
Yes, but when you condense that down, you have 1 ln, not 2. Like there isn't one in the numerator and denominator.
Okay.
Okay? So now, knowing that, can you find the limit as n goes to infinity of an? And I didn't do anything like tricky there, like applying a function to both sides. I just used simplification rules for logs, right? Do you see how it's kind of similar to the one with the cosine because I can put the limit inside the ln thing? Does that make sense? So I have ln of the limit as n goes to infinity of 2n plus 1 over n. And if I do the whole dividing everybody by n, what do I get in my numerator? 2 plus 1 over n, and then over 1, right? So that goes, the inside stuff goes to 2, so this goes to ln of 2.
So you're allowed to slide limits into the natural log?
You're allowed to slide limits into any continuous function, not just natural log. I mean, we did it with cosine too, right? Okay. Have you guys seen these really happy numbers before? Maybe. 5 factorial. So in general, a factorial, you can think about it as it either multiplies every number beginning with 1 up until that number, or I often list them down. Like, I would think about 5 factorial as 5 times 4 times 3 times 2 times 1.
Yeah.
Does that make sense? But you could also go from 1 up to 5, same thing, right? That works out to be, I think, 120. Factorial growth is something that is worse than exponential growth. Like, this is faster than exponential growth. It's sad if you're a computer programmer and your things grow factorially, then your programs blow up. Now, how is this different than that? And let's pick a specific n. Let's pick like n equals 3. So if I give you 2 times 3 factorial, how is that different than 2 times 3 in parentheses factorial? Extremely so, okay? This one means first factorial me, then multiply by 2. So that would be 2 times 3 times 2 times 1, which would equal 12, right? Versus this guy, which is
Bigger than 120.
6 factorial, which is 6, 5, 4, 3, 2, 1, or 6 times 120, which is 720. So that's why they're different. They're very, very different, yes.
So where does the factorial fall into context?
It's a multiplication. So you have to do all of this part first before you put in the 2. And if I wanted to like list those out, sort of like, because we're going to need this in like a later section. If you're listing out 2n factorial, that's 2 times n minus 1 times n minus 2 all the way down to 1. Does that idea make sense? 2n factorial. You start with 2n. What's 1 less than 2n? 2n minus 1. And then
Should there be parentheses around n minus 1?
2n minus 2. Yes, there should be. Yep, down to 1, etc.
Should there be a parentheses around just the n minus 1 inside the larger parentheses?
This guy right here, you mean?
I'm talking about over here.
No, that should not be in parentheses. Like whatever this number 2n is, 1 less than it is it minus 1.
Oh.
So there should be no parentheses here. Yep, good question. No, none at all. I meant to not put them. Do you see what he was asking? He was saying, should it be parenthesis 2n minus, like parenthesis 2, parenthesis n minus 1, which would actually be 2n minus 2, which would be 2 less, not just 1 less.
Would it be subscript to be technical about?
Nope. Just think like if this number was 6, this is 5, right? And 2n is just your number.
Right.
Just number minus 1. Even though it's 2n, it's just some number, take away 1. The relationship is if you add 1 to this, you get that back, right?
Right.
So that's the best way to think about this, I believe.
How does 0 factorial become 1?
It's later, okay? For now, that's just a definition. There's reasons it's defined that way. I'm afraid I don't know them off the top of my head, but I know to make certain things work, you have to define that way. So, yeah, I'm sure you can Wikipedia it, like it's.
Wait, everything goes back to 1, right? So if you start with a negative number, what happens?
You can't do negative factorials.
Okay.
You can't have a negative number factorial. 0 is the smallest you can go. Okay, this guy, 2n minus 1 factorial over 2n plus 1 factorial. So first we're going to simplify this. So 2n minus 1 factorial starts with 2n minus 1. What's 1 less than 2n minus 1?
2n minus 2?
Etc. Down to 3, 2, 1, right? How many numbers are in the middle depends on what n is, right? And we don't know what n is, so you just use ... for, okay, I get it, it keeps going. Versus this 2n plus 1 factorial. First, highest is 2n plus 1. What's 1 less than that? 2n. What's 1 less than 2n? 2n minus 1, and then blah, 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 3, 2, 1.
Oh, they cancel.
Yeah, bunches of stuff cancels.
Except for the 2n plus 1.
X and the 2n, right?
Yes.
We're left with 1 over 2n plus 1 times 2n, which is the same thing as 1 over 4n squared plus 2n. Do you agree with that?
And that would converge.
The limit as n goes to infinity of an is the limit as n goes to infinity of 1 over 4n squared plus 2n, which is equal to 0. So we have that the sequence converges to 0. Factorials are things that are only defined for whole numbers, like 0 on up. You can't apply L'Hopital's rule to them. Does that make sense? They're not functions. You can't, they're not the same kind, they're not continuous functions. You can't do derivatives of them.
Why is it impossible to plug in negative? Couldn't you?
They're just not defined that way. I
If
mean,
you
so,
had negative factorial, couldn't you take out negative 1 to the power of n times the factorial of n?
we're never gonna do it, so I just don't know. I mean, but the thing is, it's just never done. Maybe they're defined for specific applications, but since it says like it's this number down to 1, if you're already at -1, you're below 0. So, you know, I don't, at least with this current definition, it's not really, it's not in the domain, so to speak. Okay.
The current definition is probably slightly inaccurate.
Have you guys, no, it's not. Have you seen the squeeze theorem before? Oh, yeah. Some books call it the Sandwich theorem, with the accent, just no accent. Okay, so the idea is that if you have two functions who limit to the same thing, and you have a sequence that's in between them eventually, that sequence goes the same place. The picture for functions can look something like this. So suppose here's your L, you have your lower function, you have your upper function, and then you have another function that maybe doesn't always live between them, but eventually lives between them. So if the lower limit goes one place and the upper limit goes one place, that other function is fenced in and forced to go the same place. The only difference with sequences is that instead of continuous pictures, they're dots. Is that only defined from 0 on over, right? So to use the squeeze theorem for sequences, you've got to find the things your sequence is squeezed between. So here's an example. Tan inverse of n over n, using the squeeze theorem.
Ouch.
Ouch, I know, ouch. So let's start by figuring out what is inverse tangent stuck in between. The same thing works for its often trig functions because they often are bounds. Like sine and cosine are stuck between -1 and 1, right? Negative pi halves is less than or equal to tangent, which is less than or equal to pi halves. And I didn't just have inverse tangent, I had inverse tangent of n over n, right? So if n is positive, which it is if we're talking about sequences, right? Then we know that negative pi over 2 over n is less than or equal to tan inverse of n over n, which is less than or equal to pi over 2 over n, right?
If you just multiply the whole thing by n.
It's dividing the whole thing by n, really.
No, I mean, you're already
That takes you
there.
back to what you had, though. You care about something that's inverse tangent of n over n, so you really need to divide by n.
Okay.
And then what happens? So, and then, what's the limit as n goes to infinity of, can I just do these together and say plus or minus pi over 2n? That's the same thing, right? Where do they both go? If I have positive pi over 2n, that goes to 0. Negative pi over 2n also goes to 0. So both of those go to 0. One just goes to 0 from the bottom, one goes to 0 from the top, right? So thus, what happens to the limit as n goes to infinity of inverse tangent of n over n. Also goes to 0.
That probably shortened down a lot of work.
It's not that bad, right? So if you, and I think you could have, yeah, you actually can't use L'Hopital's rule on that fixture, on that function, because if you tried to, it's not an infinite, it's not a 0 over 0 limit. As you go to infinity, inverse tangent goes to pi halves, and n goes to infinity, so it's not of the right form. So there's no other way to do this, at least that I know of right now. Okay. But to do the squeeze theorem, you have to actually like explain yourself. Well, you can't just say converges. Yes?
And why did you use positive and negative as for your bounds?
Because I knew inverse tangent was bounded by those things. You could have picked numbers that were also, that's about, you could have also said like plus or minus 2, because 2 is, you know, pi bigger than pi halves. For things like cosine, you would use plus or minus 1, right? Does that make sense? So the first step is to figure out, ignoring the denominator, what's my function bounded by? And it's often going to happen with trig functions because trig functions are obviously bounded. Is that okay? All right. Okay, so the last thing is just a name for something. So sequences are called monotonic if the terms are non-decreasing or non-increasing. There shouldn't, that's a typo there that maybe got fixed on your notes. But basically what this is saying is that the terms are either going up or they're going up and staying level, but they don't go down as the whole, because strictly increasing means you couldn't have or equal to there. Does that make sense? Okay. So let's look at a couple examples here. Tell me whether this sequence is monotonic, and I think it's probably first smart to just list the first few terms. So what's A1 in this case? 4. Because you do negative 1 to the n, then you add it to 5, right? What's A2? 6, good. What's A3? Let's say, so this is going to be 4, 6, 4, 6, etc., right? Is that non-increasing or non-decreasing? No, it's flip-flopping. Flip-flopping is not monotonic.
Definitely monotonic.
Monotonic means it's going up or staying the same, or going down or staying the same.
Used to be a music major, and monotonic is a very dirty word to us.
Yes. Does that make sense, though? Okay. Now, this one, let's just list I'm just going to make a list and not write A1. So when you plug in 1, we got 1, right? You plug in 2, you get 6 over 4, right? Which is 3 halves. You plug in 3, you get 9 fifths. You plug in 4, you get, I got 12/6 or 2. Do you agree with that so far? So it seems to be monotonic, right? So my guess is this is monotonic, and our even better guess is that it's doing what? Increasing or decreasing? Increasing. Now, this is where Calc 1 comes back. How do you prove something is increasing? What do you use? The derivative. The derivative's purpose in life is to prove things are increasing or decreasing. That's what it does. So don't, you have to actually define a function and use the derivative. And if this derivative is positive, you know your function is increasing, and so therefore so is your sequence, right? Okay, so the derivative, use your favorite quotient rule. Low d high minus high d low over low squared. Did anybody else's teachers use that rhyme besides me? Oh yeah?
We used something slightly different. We defined the top at...
Did you use high and ho? Ho-de high or something like that?
No, we used drive the bottom. We said the bottom was P and the top was O, so it became
later. Did you guys believe that it's 6 over 2 plus x quantity squared? Does that make sense? Okay, so for any, and also we only care about positive x's because we have a sequence, and so sequence are only positive n's, right? So this thing is bigger than or equal to 0, actually just bigger than 0 for x's that are bigger than 0, right? So thus f of x is increasing, so is this little thing called Bn. Does that make sense? Yeah? Okay. So if you want to show something is increasing, you can use a list to get an intuition, use the derivative, and then to figure out from there what's happening. Okay. And the very last theorem, which I'll state, and then you can read about it in the notes because it's not super hard. So if you have a sequence that is bounded, so bounded means there's a number on top, that's its fence, or that's bounded above. Bounded below means there's a number on the bottom that fences it in. So bounded above means there's a bound above the sequence. Bounded below means there's a bound below the sequence. And if you have a sequence that's bounded, that means both of those conditions are met. So it's got both something below and something above. So like something like that might be above only. Something like that kind of thing might be above only. Or it could go the other way, because technically speaking, if I have a sequence, it would start there. So probably this is a better idea versus, yeah, this one would be bounded, anyway, okay. And bounded means both of them. And the theorem that we'll use occasionally to prove something is called the bounded monotonic sequence theorem. So if you have a sequence that's bounded and monotonic, then it has to converge. So if those terms are marching up or staying the same, your function, and you know you have a bound on top, then the sequence has to converge. It doesn't tell you what to, but it tells you that it's going to converge. So, okay.